Assalamualaikum and hi again everyone. In this session, we will look at the estimation on a single population proportion denoted by pi. Are you ready, guys? Let's go! First, let us look at the objectives of learning this topic. At the end of this session, you should be able to do the followings. Firstly, you should be able to obtain or calculate the point estimate for an unknown population proportion denoted by pi. Secondly, you should be able to construct a confidence interval for the unknown population proportion pi. And finally, you should be able to interpret the constructed confidence interval for pi. Let us now learn on the point estimate for an unknown population proportion denoted by pi. The question is, what is the point estimate for the unknown parameter denoted by pi, which represents the proportion of success from a single population? Pi can also denote the proportion of failure depending on the question that we want to solve. The answer to this question is simply the sample proportion of success or failure that we can identify or recognize from sample information, or we can calculate from a set of sample data if its value is not given directly. We denote the sample proportion using a small Roman letter P, where P is given by x over n, where x is the number of successes or the number of failures in sample, and n is the sample size. Look at example 3.3 in the textbook, page 71. A manufacturer of printed circuit board (PCB) is interested to estimate the fraction of defective units produced. A random sample of 200 boards contains one defective unit. Here, the word fraction is another terminology that we can use to represent the proportion. The question that we want to address in this slide is, what is the point estimate of the true or population proportion of defective units produced by the manufacturer? The answer is rather straightforward. You can obtain the point estimate of the fraction or proportion of defective units produced by the manufacturer by calculating the proportion of defective units from the sample data denoted by P. Here, P is defined as the number of defective units in the sample denoted by X over the sample size denoted by N, Replacing the values of x and n, we have p equals to 1 over 200, which is equivalent to 0.005. If we are interested in estimating the true or population proportion of non-defective units produced by the manufacturer, then we can simply get the complementary value of P, which is 1 minus 0.005, resulting to 0.995 as the estimate of the population proportion of non-defective units produced by the manufacturer. Now, let us look at the confidence interval for the unknown population proportion pi. You may refer to the textbook pages 71 to 72 for more detailed explanations. Using the same approach that we did in constructing the confidence interval for mu, we may recall materials that we have learned in Chapter 2 on sampling distribution of P. We knew from Chapter 2 that when the sample size is large, that is, when the sample size is at least 30, the sampling distribution or P, or the distribution of sampling proportion of success or failure, is approximately normal with mean pi, the population proportion, and the variance pi multiplied by 1 minus pi over n. The standardized random variable z is given as p minus pi over square root of pi times 1 minus pi over n. Again, the sampling distribution of P and the standardized Z formula are both provided in the statistical table and formula in pages 2 and 3 respectively. Our focus here is on pi in the numerator. And let this pi in the numerator be our parameter of interest. Leaving pi in the numerator alone, we have the following expression. Pi equals to P minus Z times square root of pi times 1 minus pi over n. Do you agree with me? It is obvious, isn't it? By borrowing this formula, we can then construct the confidence interval for the unknown population proportion of success or failure denoted by pi that I will explain in the next slide. Previously, we knew that pi can be expressed as P minus Z times square root of pi times 1 minus pi over n. Now, by borrowing this expression with little modification, we can then obtain a 100 times 1 minus alpha % confidence interval for pi given by this expression, which is the small p plus minus small z alpha over 2 times the square root of small p times 1 minus small p divided by the sample size n. Notice here that the capital P which represents a random variable sampling proportion in chapter 2 now changes to a small p, which denotes a point estimate of the population proportion, which is simply the value of the sample proportion. The minus sign now is replaced by a plus and minus sign. The capital Z, which was previously a random variable, now changes to a small z, representing a value of z at alpha over 2. Whereas the notation pi in the square root is now changed to small p, that is the value of sample proportion that we use as a point estimate of pi. It is important to realize that when we want to estimate an unknown parameter such as pi in the slide, then by right we do not know its true value. That is the reason why we want to estimate its value by using sample information. Hence, there should not be any pi in the confidence interval formula. Therefore, the unknown population proportion in the square root is replaced or estimated by the sample proportion value P. It is worth noted that in this topic, we only consider a large sample size, that is, n value is at least 30. We do not cover the case with a small sample size. Second, as mentioned earlier, the proportion from population pi is in the square root should not be used in the confidence interval formula. Instead, it is estimated by P. And finally, unlike constructing a confidence interval for mu where we had 3 cases, here we only have 1 case. That is, in constructing the confidence interval for the unknown population proportion of success or failure, we only use Z in the formula, besides the sample proportion P and the sample size N. Alternative expressions for writing the 100 times 1 minus alpha percent confidence interval for the true population proportion pi are as follows. Either you can write like this, where the inequalities are written in the middle with pi stated clearly, or you can use this expression where we can use the open bracket and close bracket directly for the interval, but without writing the notation pi in the middle. The 100 times 1 minus alpha percent confidence interval for pi also refer to the probability that the lower limit p minus z alpha over 2 times the square root of p times 1 minus p over n and the upper limit p plus z alpha over 2 times the square root of p times 1 minus p over n contains the true parameter value of pi is 1 minus alpha. Let us look again at example 3.3 in page 71, related to the proportion of defective units produced by a manufacturer of printed circuit board PCB. We are still dealing with a random sample of 200 boards containing one defective unit. The question this time is, find the 90% confidence interval for the true proportion of defective units produced by the manufacturer. To answer this question, we may follow the steps that I suggested in earlier session when we dealt with constructing the confidence interval for an unknown population mean mu. Let us recall the steps in the next slide. The steps that we will use in solving example 3.3, page 71 are as follows. The first step is to recognize the information given in the question. What do we know from the question? Here we can list down the information using correct notation, and we can see that the number of defective units x is 1, the sample size n is 200. Therefore, we can calculate the point estimate for the unknown population proportion of defective units denoted by P, which is equivalent to x over n. Substituting the values of x and n, we have 1 over 200 equals to 0.005. The next step is to identify the parameter of interest. Here we are interested in finding the confidence interval for the true population proportion of defective units, denoted by pi. The next step is to choose the appropriate case if relevant. As we know we only have one case in constructing the confidence interval for pi, that is, to use Z in the formula. And finally, substituting all the required values accordingly, we can then solve the question. Therefore, a 90% confidence interval for the population proportion of defective units is P plus minus Z alpha over 2 times the square root of P multiplied by 1 minus P divided by the sample size n. Here Z alpha over 2 is Z 0.05, where 0.05 is alpha over 2, where alpha is 10% since we have a 90% confidence interval. Substituting all the values in the formula, we have the final answer. Here 1.6449 is the value of Z alpha over 2, that is Z 0.05 obtained from table 4 in page 34. The 90% confidence interval for the true population proportion of defective units produced by the manufacturer is negative 0.0032 and 0.0132. The answer is mathematically sound, but in practice, you can report that the 90% confidence interval for the true proportion of defective units produced by the manufacturer is 0 and 0.0132. As we know, proportion value should never be negative in practice and should never be more than 1. Now can we look at task 3.8 in page 72. The question gives us this information. A random sample of 400 components were tested and 6.25% of the sample components failed to satisfy product specifications. The question is, find a 90% confidence interval on the true proportion of components that fail to satisfy the specification. As we can see here, 6.25% is another way to express the proportion of sample, which can be expressed as 0.0625. So how are we going to solve the question? Again, we can repeat the 4 steps in answering the question. First, recognize the information provided in the question. What do we know from the question? Here we notice that the sample size n is 400 and the sample proportion of the components that fail to satisfy product specifications is 6.25% or 0.0625. Next, we identify the parameter of interest. Here, clearly, we are interested in constructing the confidence interval for the true proportion of components that fail to satisfy the specification. Notice that the definition of P and the definition of pi must be consistent. If we want to construct confidence interval for the proportion of components that fail to satisfy the specification, then we should use the sample proportion of components that fail to satisfy the specification. On the other hand, if we are interested in confidence interval for the true proportion of components that satisfy the specification, then we have to use the sample proportion of components that satisfy the specification. Then we identify a suitable case relevant to this topic. We know that we only have one case related to constructing the confidence interval for pi. That is, we should use Z in the formula of confidence interval. Therefore, 90% confidence interval for the proportion of components that fail to satisfy the specification is given as follows: P plus minus Z 0.05 multiplied by the square root of P times 1 minus P over N. Here, Z alpha over 2 is Z 0.05, as we know alpha is 10% because we are constructing a 90% confidence interval. Therefore, alpha is 10% and Z alpha over 2 is simply Z 0.05. The value is 1.6449 from table 4, page 34. Substituting the values that you obtain from the sample information, then the answers for the interval is 0.0426 and 0.0824, or simply 4.26% and 8.24%. What can we say about the value? We can say that we are 90% confident that the interval 0.0426 and 0.0824 contain the true parameter value of the population proportion of components that fail to satisfy the specification. Or simply the probability that the interval 0.0426 and 0.0824 may contain the true pi value is 0.9. I repeat again the interpretation for task 3.8 that we have looked through in the previous slide. We knew that a 90% confidence interval for the true proportion of components that fail to satisfy the specification was 0.0436 and 0.0824, or 4.26% and 8.24%. What is the interpretation based on this answer? First, we may say that we are 90% confident that the interval 0.0426 and 0.0824 may contain the true value of pi, which is the proportion of components that fail to satisfy the specification. Alternatively, we may say that the probability that the interval 0.0426 and 0.0824 may contain the true pi value is 0.9. Before we end this session, let us do a checklist on the objectives that have been listed in the beginning of this session. Are you ready? Okay. Let's look at whether you have achieved the first objective. Are you now able to obtain a point estimate for the unknown population proportion of success denoted by pi? As we know, pi can also denote the proportion of failure depending on the question that we want to solve. This is quite straightforward, isn't it? The point estimate for pi is simply the sample proportion of success or failure denoted by P. What about the second objective? Are you now able to construct a confidence interval for the proportion of success denoted by pi? Remember, we only have one case in constructing the confidence interval for pi, which involves Z alpha over 2 only. If you are still not sure, I suggest that you repeat watching this video again to grab the fundamental concept on the confidence interval for the population proportion. Finally, are you now able to interpret the confidence interval? I really hope that you will achieve all these 3 learning objectives on the topic. Please have a go and try more questions in the textbook exercise 3 and supplementary exercise 3 for a better grip on the topic. I wish you all the best. Wassalamualaikum warahmatullah and have a good day.